example, and kind of the overall concept. And then Monday, we'll spend more time probably going through 3 or 4 examples. We'll see how that goes. And let me see. Is there anything else going on? I have not seen. Sorry, I certainly don't want to worry anyone unnecessarily, but maybe an hour ago, there was a notification from Boulder Police about a possible bomb threat around Pearl Street. So if you're not in the Pearl Street area, I think near the shopping area, or if you have a chance, maybe just check out their Twitter feed real quick if you're anywhere near there. I just want to make sure everybody's safe. So I have not seen any notification from the university. Maybe it's far enough away. They don't care. I'm not really sure how they decide what kind of information is transmitted through their communication processes. But if you want to take a moment to just see if you can find some information about that, feel free. Okay, and I'll take a slow moment here then to get my share going and so forth. Give you guys time to do that. Okay. All right. This is the same cover slide or front slide that we had last Thursday before the exam, but we're now working through this moment of momentum concept that we'll be talking about today. The announcements, I'll just run over the extra credit real quick again. I did send an email this morning. There was a strange problem where people who had signed up for the registered for the symposium did not get the email with the link info. So I just went ahead and sent out the blanket link to you guys. So if you haven't looked at your email and you didn't get one after registering, please feel free to use that connection info. Homework 10 is posted due next Thursday. It has the typical 8 problems from Wiley Plus, 2 written problems. I feel pretty good about all those. Emma will hold her off. No. Alexi will hold his office hours on Monday, and Emma and I will hold ours next Wednesday, kind of back on regular track. And real quick then, just to remind you, the extra credit sort of going on right now, the Hydro Symposium started this morning at 8:30. It goes through tomorrow at 5 or 5:30, and basically 8:30 to 5 each day. We've had, upwards of, I think we had over 100 participants registered. We have had kind of 30 to 40 folks in different talks, so it's been really good so far. So I encourage you to take advantage of this. And the turn-in now is on Canvas. It's just called Extra Credit, and it's under the homework. If you go to assignments in Canvas, it's under the homework module, I guess. Right now, just one thing to tell you, it says 0 points because what I didn't want Canvas to do was look at that, and if you didn't turn anything in, penalize you for not getting any points. So instead, by giving it 0 points, whatever points we assign when we grade what you turn in will be added overall. Okay, so it truly does look like a bonus. But I just wanted to make sure you understood that 0 total points that are possible it was not really an error. It's just a way of us tricking Canvas to do what we want it to do. All right, any questions before we get going? Emma or Alexi, do you guys see anything in the chat? I wasn't paying attention there.
Nothing in the chat, just someone put a link to the symposium schedule. So.
Oh, great. Thank you. Yeah. Okay, wonderful. All right. So building on this notion of the conservation of momentum that we started last week before the midterm, we're now going to start looking at this moment of momentum. Okay, so momentum, of course, has a vector component to it because it includes the velocity vector, right? And now we're going to think about what happens if we take the moment of that momentum. So in other words, we're looking at momentum sort of, we're conserving momentum again, but now we're doing it sort of I'd actually not thought this is a pretty good pun, at arm's reach, right? Now we're thinking about like sprinklers turning the arms that have to go out to the point where you have an axis in the middle that moves water up and out to the arms. And then there's some length at which the velocities all occur away from the center of the where the water comes up the main axis. Okay, so let's just start with this very simple diagram here. And when we start to, let me get my pen going here. When we start to talk about the moment of momentum, we automatically want to start thinking about torque. Oops, T-O-R-Q-U-E, wanted that U to come early. And torque, so torque has this definition here, but R is a vector. It's some radius away from some point at which torque would be occurring. And then we do a cross product with some force vector as well. Okay, pardon me. Yeah, I guess a force vector, we call it that. If we were mechanical engineering students, we might start to think very carefully about the impacts of torque on roto machinery of some kind. In the context of civil engineering, we do this more in the context of thinking about pumps or other machinery that would be in line, but we're sort of focused on the bigger system. Now, if you end up taking the hydraulics course from Dr. Newpower in the fall, that course will go into pump design to some extent. And the torque will be very important because you end up coming back to sort of looking at balancing forces, flow rates, and energy production or energy use in power production, power use in these different pieces, I guess, of an overall system. So when we think about dam electric production or something like that, hydroelectricity. All right, we also have to start with thinking about something called angular momentum. So fundamentally, momentum is mass times velocity, right? Our angular momentum, we simply take our radius, some radial vector, and we cross multiply it by this m times v, which is obviously a momentum, and the v, of course, will have a vector notation to it. Let me just show one little thing. We can rearrange the angular momentum equation slightly to indicate that basically this R cross MV is equal to really just R cross V, right? Those are the two vectors. M is a scalar that we could just leave outside, essentially. Okay, so when we're trying to do cross product work, our multiplication through here with these cross products, we will end up doing that with the vectors more so than the scalars. Okay, so we had this equation when we were deriving the momentum conservation equation from Newton's second law. And it basically said that the sum of the forces acting on the system are equal to this derivative of the integral of momentum of our system. Okay, and that's more or less we could then take this a step further and say equals the momentum stored within a control volume plus any exchanges across the control surface of momentum, right? So if we extend this equation to the moment of momentum, we would basically have something that looked like this. The sum of these torques now, R cross F, vector F, for the system is equal to d dt, so this big derivative with respect to the integral over the system of R cross V, and then outside we're going to keep rho and dV, and remember this V with a cross through it is the volume, right? So this is essentially looking at the moment of momentum as it's summed outside of this system or acting on the system is equal to this derivative of the integral of the moment of momentum for the system itself. Okay. All right. Okay. I'll give you guys a second and just make sure you've got that. And we'll move on to expanding this in the same way I described expanding this one above, right? So we will start to now look at what it means to store this and what it means to have exchanges in and out of a control surface. Okay, so we can again use the Reynolds transport theorem. Remember that when we did this in sort of the most generic way, we said D B-sys, so this capital B was our intrinsic characteristic, and little b was an extrinsic characteristic. And we could then break this down to look at del B, change in whatever B is in the control volume with time, plus the outflows minus the inflows, right? And so in our case now, we're going to take this this B-sys to be the system moment of momentum. So we're going to represent it this way, which is what we did on the previous slide. Then BCV, the moment of momentum in the coincident control volume, is now going to look like this. Okay, so that looks the same as above. The only difference is that we're just looking at the control volume component of that, so what's stored there. And then little b is this moment of momentum per unit mass. And so we just end up with R cross V. So what does this look like? So this gives something like this. And I'm going to try to write kind of thin because it's a pretty long term, but I'll try to give myself a little bit of room in case I have to go to a second line. So d dt, the integral over the system of the radius vector multiplied by some velocity vector times rho dv. This is the system component. So this is the left-hand side here, okay? Let me try to get clever and do some color coordination. So then this component here we'll write in blue. So we say this equals del t of the integral over the control volume of the stored moment of momentum. So R cross V rho dv, and again, the v with a cross through it is not velocity. This is now volume. And then let's look at the exchanges. So now, let's see, we'll go with green. So let's do the outflows first because that's the sequence we're going in. So we're going to add the sum of rho out times v out times a out. And you're probably wondering, well, that seems kind of lame. We've done that already. That is essentially these three pieces. Now we have to add the little b component. And so now we multiply this by r cross v. And then I'm just going to put an out here. Okay. And then finally, pen color, do something that shows up a little better. We'll go with black. All right, then this last term here will be all of the inflows. So then we subtract the sum of rho in, v in, a in, and remember that's more or less a mass flux coming in multiplied by, again, R cross V for all of the inflows, okay? So there's a long, kind of ugly equation, but because we've been building on the Reynolds transport theorem for the past couple of weeks, it's not so far out of the realm of possibility, right? I mean, the only difference between this and the one that we wrote last week for momentum is simply that we have this R cross included now, right? We had V, some vector of velocity represented in this equation last week for momentum. Now we're including this R cross as well. Okay. So let's go on to the next slide. Well, I'll take a sip, make sure everybody's caught up here. Okay. So the interpretation of this expression, so these are the four pieces we just wrote on the previous slide. The left-hand side was the top term. This was the first one on the right-hand side, and then these are the second and third on the right-hand side, right? So essentially, this term is the rate of change of system moment of momentum. Okay, I guess I should have probably kept up my my colors the same way I did on the previous slide. Sorry about that, but I'm going to go ahead and change color for this one. What was our second one? I think it was red. What did I do here? No, we were red then blue. Okay, so the second one here that's blue is this first term on the right-hand side now. This one, its interpretation is the rate of change of the moment of momentum in the control volume. So we know that in part because the integral is only done or evaluated over the control volume. That little c sub v tells us that this is about storage within the control volume as opposed to the entire system in the top, what's indicated in the top term in this case. And then finally, let's see, I used black on that one. I guess we'll go with green to just indicate that these two are about overall, these last two terms are about the net flow of the moment of momentum. Across the control surface. Right, and we know that in part, I guess we know that mainly because we have ins and outs noted, but if we had left it in integral form, of course, the integral would have been taken over C sub S for evaluation rather than sort of these ins and outs, right? Or rather than CV, rather than CIS. So that's one clue to sort of think about what each of these terms mean is looking at over where that or what that integral is being taken or evaluated. And then in the case of the ins and outs, clearly we're looking at the fluxes across the control surface. Well, I'm not real fond of how light that green is. I'll try to stay away from that. That's not a lot of contrast there with the background being white. So, all right, so let me change my color. Was there a question?
Yeah, we just have a question in the chat. Just kind of what are the units for R cross V?
So let's see. So it's just going to be, so it's like a moment. So, oh no, wait, sorry. Just R cross V is going to be meters or length squared per time. I was thinking back to torque. Torque is going to be like a force times the length, which we had written on the first slide today. Great. Okay. So the expression from the Reynolds transport theorem will be, let me move this out of the way, will be the right-hand side of the previous expression for Newton's second law. So in other words, we can write this sum of R cross F. So this is the torque part of it, or moment part. The system is equal to d dt of the integral over the entire system of the contained, or what moment of momentum is included. Okay, so then the left-hand side of the expression for the second law, Newton's second law, will be the sum of the moments and the coincident control volume. So what do we mean by that? Essentially that the sum of R cross F of the system is equal to the sum of R cross F for the control volume as well. Okay, when we're coincident in that control volume. So if we substitute both of these things into the long equation that we wrote on the previous two slides, or we wrote it 2 slides ago, we interpreted it on the last slide, it looks like this. We're going to have the sum of R cross F over the control volume is equal to del t of the sum, or the integral over the control volume, that's supposed to be a v, all right, of R cross V times rho dV. So this is the control volume plus the sum of the rho out, V out, A out, times our R cross V also going out. My U's are not coming through. Sorry about that. All right. And then we subtract the sum of the inflows, right? So rho in, V in, oh, come on now. V in, this is supposed to be velocity, not volume. A in, written very deliberately, still didn't get it. Okay, multiplied by R cross V on the inflow. Okay? So we've evolved this a little bit to move, we still have forces on this left-hand side, but now we're sort of looking at the forces acting on the control volume rather than just the system overall. So we've kind of substituted those, but this is in the case of thinking about the system being coincident with the control volume. All right. So on the next slide, we're going to look at what happens when we have steady flow, how we simplify, and what happens when we, of course, account for being incompressible. And in which case, of course, rho out equals rho in, right? So we can simplify again. All right, so let's do that. The next slide. This was something we did with momentum as well, but now we'll do it with a moment of momentum. So now we have, when we have steady flow, remember that this part here, there's no change in time, right? So that term is essentially going to go away. And what we end up with then is the sum of R cross V acting on the control volume as being equal to just the exchanges across the control surface. So the sum of rho out, V out, A out, multiplied by R cross V out, and then subtract the inflows. Yeah, okay. I think I have one little error in my notes, but I think I just identified it. So let me try to avoid it here. Rho in, V in, A in times R cross V in. Okay? And then if we also assume that we have incompressible flow, then we don't get to just ignore the rhos, but we can't just call them a common rho value, right? So the density, if it doesn't change, it's not necessarily we have to call it an in and an out. If they're equal, we will just call them rho. So we still have to include it. So what we end up with then is the sum of our R cross V's acting on the control volume. Acting on the control volume is equal to, now we can write this in a little more summary way, sum of the outputs of rho times Q times R cross V, and then we subtract the sum of the inflows of rho times Q times R cross V as well. Okay? So all we did was simplify that because the rho is the same for whatever fluid we have coming in and going out. And we got rid of that temporal term as well, still gone because we had the steady flow condition and incompressible flow. All right? Okay, so I think this will make a little more sense when we start to look at some diagrams and so forth when we put this into motion to put to use. First, I just want to talk a little bit about angular momentum because we have to deal with some velocity nomenclature, for lack of a better term, which is to say that sometimes things are spinning in one direction, but they have outputs of velocity going sort of in the opposite direction. And we need to think about which of those impact the velocities that we have here. Which velocities are we going to use for the V and for the vector V components in this equation? All right. So angular momentum here, we are interested in relating the torques or force moments to angular momentum. For example, what torque flows from a rotating sprinkler, does the flow from a rotating sprinkler cause, is a reasonable question. All right, so let's take a real simple sprinkler. We have flow coming in down at the bottom. Obviously, it goes up the shaft here, sort of the center axis, and then it gets distributed out each of the two arms. And what you can see is that omega is telling us that we are spinning, if we do the right-hand rule, we're spinning sort of in the upward direction, right? But the flow is coming out in the opposite direction, right? The sprinkler head itself has a velocity in that direction. The flow is going in the opposite direction, or the velocity of the water is going in the opposite direction. So how do we resolve this? So a couple of things to note. We're gonna break this apart a little bit, but first note that we are looking at these E hat values are simply the unit vectors in this other sort of direction where we're thinking more about radial coordinates, right? So we're looking at R as a radius away from a center of rotation. And when we look down from above, we can think about this head here having some W1, W2 in both cases. We've got this W1 is often indicated at the inflow, and there's no spinning there, so 1 is sort of ignored. And then we expect that we are evenly splitting the water into whatever number of arms we have. So in this case, for this sprinkler, we have 2 arms. So for whatever flow comes in the base, we're evenly splitting that in half to go down each of the 2 arms of the head of the sprinkler. So U is indicating the velocity of the head itself. V is indicating the velocity of the water coming out the backside. Okay, so if our control volume is sort of defined by this plane in which the heads are spinning, we need to think about these v theta and a u being this r2 over omega value. So omega is indicating basically this angular velocity. All right, so omega is, I think I defined these actually on the next slide. Yeah, I've got these defined a little better on the next slide. So omega is our angular velocity. And it's often, I think that one is going to be given in sort of rotations per time, like an RPM, something like that. And then the actual velocity, and so that just tells us something about the spin. You can see that the torque about the shaft is going in the same direction as omega, as this angular velocity. But the angular momentum is dealt with by looking at W, V, and U out at the edges. So let's relate all of these things on this next slide. Curious. Okay, here we go. So the simplified form of this is that the shaft torque, or the torque about the shaft, is equal to minus m dot in, so that's just rho times q, right, times plus or minus r in v theta in, and I'll define each of these below, plus m dot out plus or minus r out v theta out. Okay, so T shaft is obviously the torque on the shaft. This m dot is our mass transfer rate, so it's density times flow rate, right? Rho times Q, which is positive for flow out and negative for flow in. So those rules are defined by sort of the original Reynolds transport theorem, right? Whether that sign is negative or positive. And then we have R in is the perpendicular distance between the axis of rotation and the point where the mass flow enters the control volume, right? So R in is usually, for a sprinkler, R in tends to be small or zero because you're putting water directly up that shaft. It doesn't have a radius away. It comes up in the axis itself vertically. And then R out, oh, goodness sakes. Come on, make it an R. I don't like that. R out is the perpendicular distance between the axis of rotation and the point where the mass flow exits the control volume. So now we're looking at essentially the length to get out to where the sprinkler head is spraying the water out. And then finally, V theta, we could have it in and out, but V theta is the tangential component of the absolute velocity entering or exiting the control volume. So this is critical simply because the direction of this, if it's tangent to the circular path of the sprinkler head, we need to account for, a component acting perhaps only tangent to that circle, right, in the R direction. So we're working now in these this framework that is radial coordinates. All right, so let's look a little closer at our sign convention here now. I have these pluses and minuses. What do we do with the R's? We know what we do with the ins and outs here. What do we do with this the sign convention on these pairs? So to determine the sign.
We just got a few questions from a couple slides back. I don't know if we can answer them in a second.
Sure.
Yeah.
Where to?
One more back than this.
Oops. Let's see. There. This one.
Yeah. Someone says, isn't the sum of R cross F for the CV part, so I'm not quite sure what they're asking there.
Oh, on the left-hand side, did I goof that up? Let me see.
Um,
Yeah, I was just saying it was R cross F to 0, R cross V. CV.
Yep, you're right. I did.
yeah.
I made that mistake twice. So it's funny because, so yeah, thanks for catching that. Okay, so it was funny because in my notes I had this one wrong as an F, and I knew that was incorrect, but I did not catch that I could completely goof this one up. All right, this should be, my apologies. So this should be R cross F. Yeah, so this is the torque, and this should also be R cross F. Sorry about that.
And then also people are just kind of asking to kind of clarify the differences between momentum, moment of momentum, and angular momentum. But I know we're kind of going through that as well.
Yeah, so the angular part of this is simply that we have something that is spinning. So the classic example to get this idea across is using sprinklers as some kind of a what do you call it? An example, but ultimately we could be looking at forces that are acting in any direction that gives us a torque, right away from the sort of the where the system works its way through. So in the control volume that we have for these sprinklers, essentially we're including the whole plane through which the sprinkler heads turn. So we end up going with the angular part of this. The linear part of this could just be a simple, that R doesn't have to be a radius, right? It could be something else. We just don't have a ton of great examples for those, are like an X cross V or something like that. So we stick generally with these sprinkler head examples. So sorry, that may not be super satisfying, but that's essentially, so we kind of quickly translating from moment of momentum into this angular component of it right away. All right, anything else, Alexi? Did I miss there?
I don't think anything else. Yeah, no other questions.
Okay, cool. Jump back ahead here. Okay. Okay, so we need to consider the velocity of the rotating body U, and U here is going to be equal to R times omega. So this is, R is clearly the distance from the rotation axis. And then omega is the rotation speed of the shaft. Okay, so that's those two values coming together to give us the velocity of the rotating body, right? The speed at which a sprinkler head is moving in the plane that it's moving. Now we're going to use plus R times V theta when V theta and U, now V theta is this tangential velocity, and U are in the same direction. Otherwise, we're going to use the negative version of this, negative R times V theta. Okay? So it all just matters whether V theta and U are working in the same direction or not. And then this shaft torque is positive if it's in the same direction as W, capital W now, not omega, capital W, and negative otherwise. So in this case, this capital W here, this is essentially indicating our momentum that's coming out the end. And that is, let me see, let me get this. I think I'm jumping ahead just a little bit here, but W essentially, this capital W is the fluid relative velocity. Now, what do we mean by that? Well, it's about this sort of, difference in a way between U and V, essentially acting in opposite directions. So W is sort of the resultant in some way. So let me define that on the next slide. After the sign convention, we'll talk about, let me make sure I've got this right. Yep, we'll have the tangential velocity that we'll define here, and this V sub theta. All right, so V theta, this tangential velocity, is equal to W plus U, and capital W, as we said, was the fluid relative velocity. And U, capital U, is the rotating body's velocity. So that's why on the previous slide, when I wrote W, capital W, it's the difference between, if we algebraically moved U to the left-hand side, it would be V theta minus U, right, is this difference, the balance then for for this velocity. Okay, so for all of the angular momentum problems that we're going to solve in this class, we'll use this fairly simplified momentum equation, which I wrote out on the previous slide. So sorry, I guess we're just going to T shaft, the torque for the shaft is equal to minus m dot n times the plus or minus r in v theta in plus m dot out times plus or minus r out v theta out. And I'm not quite sure why that went away, but let me just include this just to note, again, this relationship here for these guys at the top, this definition of v theta, I guess the theta is actually used over here, but in any event, W, capital W is the sort of product or dependent on v theta and U. And then we're going to use that v theta when we get down to calculating the shaft torque. Okay, so the next thing I have queued up is to just go through an example where we're going to put all these things together using this shaft equation and then, or the torque equation, and then we're going to go through how we calculate v theta and so forth. All right, so hopefully this will all culminate a little better, because I realize it feels very nebulous without a little more concrete demonstration of where these velocities lie, how they relate to each other, and how they help us figure out something like this torque on the shaft. Okay, so here's our example. We have 5 liters per second of water entering the rotor shown along its axis of rotation. So this is that, 5 liters comes in, it goes straight up the shaft, and then there's a cross-sectional area of each of 3 nozzle outlets is 18 square millimeters. So how large is the resisting torque required to hold the rotor stationary if theta equals 0 degrees? In other words, we're going to look down on this. Let's see, do I have a better picture? I don't. Okay, so this is See right there, that's where theta is defined. Theta is essentially an angle that says that it defines sort of whether you're tangent to the line of this radius or whether you are not tangent to that. So it's sort of the degree of tangentiality, let's say. And so if theta is equal to 0, then these are probably scooped back a little bit, and they are simply set up in a more streamlined way to go with this rotation. All right, so let's see. The first thing I want to do, what we're really being asked for is not so much, well, in an indirect way, we're being asked what is the shaft, the torque on the shaft that's rotating. Because the way it's being asked is how much torque would you have to apply in the opposite direction to keep that head from spinning around. So a couple of things. One is the flow that we're going to take is we have 5 liters per second. It's going to come up the middle, and we're going to assume that it gets evenly distributed into these 3 arms. So the flow out of each one of these will be 5 liters divided by 3. Okay, so that's a simplifying assumption. We don't have to worry too much about that. Secondly, let me write out this T-shaft equation again. This is fairly common in these sorts of problems. Equal to minus m dot n times plus or minus r in v theta plus m dot out times plus or minus r out v theta. And the one thing I want you to notice is that because the inflow to the control volume, so if the control volume is defined by these 2 red circles, that are bounding the top and bottom of the arms of the sprinkler, then the water that's flowing in is flowing up with R equal to 0, right? It's flowing up the axis, the vertical axis of rotation. So what that means then is that this whole term goes to 0, right? If R is equal to 0, this whole term equals 0. And as it turns out, V theta would end up being 0 as well, only because there's not a direction of velocity that's in the R direction. It's all in the Z direction here, the vertical direction. So this simplifies things. And now we're just looking at the shaft torque being equal to the outflowing, essentially moment of momentum from each of these 3 arms. Okay, so that's where we're going to go next as we work this out. So I'm going to move to the next slide. Oh, I did not copy over the image on the next slide, but I think it will be fairly straightforward. So the other thing that we need to do here is note that on the previous slide here, let me get my image back. This theta that we identified on the next slide has, something to do with this this direction of flow, and with the way we are defining that angle, theta here. If what we really want is the cosine of that angle, right? So we're going to modify this equation slightly to include cosine of theta, simply because we've been given the information about whether this is coming through sort of at an angle to the circle that we're spinning through, or whether we were coming just sort of straight out, right? But we need a component that ultimately tells us something about what's going on at the head of the sprinkler. So let me just rewrite this. So step 1 here is to rewrite this simplified. So T shaft is equal to m dot out times R out times V out, or V theta. Oh, actually, this will just be V out times the cosine of theta. So in other words, we're changing V theta to basically be V out times cosine of theta. All right. Okay, so that's the way that we're re-representing V theta here. Now I've left the cosine outside of this this parenthesis. I didn't have to. I could have written it inside as well to purely replace it inside the parenthesis. But in any event, we have this to work with. Okay, so what is m dot out? We said m dot out is equal to rho times q, and in this case, we're given 5 liters per second. Yeah, 5 liters per second, and we multiply by, let's see, we are working in metric, so we would have, let's see, 1,000 kilograms per cubic meter. So we can, let me think. So this is going to be equal to, I'm not going to do the conversion yet. Let me just leave it in these terms here. 1,000 kilograms per cubic meter multiplied by 5 liters per second. Now, I know that eventually, when I put it into this equation up top, the T shaft one, I will then put in the conversion. But just noting that we have that is helpful, and all we need to do is work on a conversion. Okay, now what about V out? So we know what R out is. R out is the radius to get out to the head. And in this case, we were given what, R is half of a meter. All right, so that's pretty big. So we're given that R out is equal to 0.5 meters. So we know this. We've just calculated this. I mean, we get a final number. We're given the cosine of theta. We know that theta is equal to 0 in this case. So we just need to calculate a V out. Okay. Now, V out is only complicated by the fact that we're taking all of that 5 liters per second and splitting it out in 3 ways, right? So V out is simply going to be equal to Q divided by these 3 times the nozzle areas, right? So it's only 1 Q, 5 liters per second, and the velocity that's coming out of each one is essentially that Q divided by 3 of those areas at the edge. Okay, so this would be equal to, again, we can do the conversions, but 5 liters per second, just as a check to know if we have everything, divided by 3 times 18 square millimeters, right? So we need to convert that to meters, and we'll have to convert our liters per second into meters as well, and we can work this out. So if I rewrite this now, before I do all the substitutions, let me take one step to simply say that T shaft is equal to rho times Q squared times R out times the cosine of theta divided by 3 times these nozzle areas. Okay, so granted, I've taken the step of kind of putting in the these values already. So on the next slide, we'll go ahead and put all the numbers together and the conversions to be able to calculate a value. So I'll give you a second to catch up. Just make sure we're all at the same point. And by the way, this is the next slide, next 2 slides will be fairly brief, and then I'll have 3 of our conceptual questions to ask after that for participation. So if you need to get your iClickers ready or your Reef app, go ahead and get those going. Okay, so here's our shaft equation now, the torque on the shaft, and we end up with T shaft is equal to 1,000 kilograms per cubic meter. And we multiply by 5 liters per second. That quantity is squared. We multiply by 0.5 meters for our radius out. We multiply by the cosine of 0 degrees. And then we multiply by 1,000 millimeters. Oh, this is for the denominator here. Let me write that in. 3 times 18 millimeters squared. And this is 1,000 millimeters in 1 meter. We're going to square that for the denominator. And then for the numerator, for these liters per second, we can just divide by 1,000 liters per meter cubed, right? And so when we multiply this out, we end up with this shaft torque as being equal to 231 Newton meters. Okay? So that's how much torque you would have to apply to keep the head from rotating. It's also the amount of torque that is generated by putting this 5 liters per second through this particular sprinkler. Okay? Now, a quick question before we finish this example altogether. Cosine of 0, of course, is just 1, right? So an interesting question would be to ask, what happens if theta is greater than 0? In other words, if that angle is not sort of perfectly aligned with the tangent and it comes a little further out and out and out, maybe it's 30 degrees, 60 degrees, what happens then? Well, let's just look at the equation. If we start to increase, let's go from 0 to 90. If we increase the angle, cosine theta, of course, right, if we make it like 45 degrees, that's going to be less than 1, right? In other words, the cosine of 0 is equal to 1. Anything, any angle between 0 and 90 degrees is going to be less than 1, which means that the torque goes down, okay? So the overall shaft torque that would be calculated will decrease whenever that theta angle increases between 0 and 90, all right? Okay, so let me just make a note of that. So T shaft decreases because AUSE, because cosine of theta greater than 0 is going to be a value less than 1. In other words, it's maximized at theta equals 0. So this makes sense because a smaller proportion of the velocity would be tangent to the axis of rotation. Essentially, that's how we can interpret that. Okay, the last slide I have here is to just relate torque to power. Power as an important aspect when we're thinking about pumps or other types of roto machinery. Sometimes we have to think about the power that's required. So we often want to talk or want to know the shaft power related to the system, and we write that as W dot shaft subshaft. So this power for the shaft is equal to the torque of the shaft, or acting on the shaft, multiplied by omega, the angular velocity, okay, or the rotation velocity of the shaft itself. So we can also write that as W shaft, I realize there are a lot of W's here, apologize for that, is equal to M dot N times plus or minus R omega V, that's not supposed to be there, V theta N plus M dot out of plus or minus R out times omega times V theta out. Okay? So all we did was take that omega and distribute it inside of these two terms on the right-hand side that we had expanded before to talk about that shaft torque. Okay, so now I've got 3 conceptual questions to go through. So any questions on this before we do that? Yeah.
Just a few questions on the last slide. First is should the answer be in kilonewtons?
Let's see, kilograms. Well, let me do the math real quick. So the 1,000 in the top and the 1,000 in the bottom will cancel out, right? Just as far as magnitudes go. So 1,000 times 5 times 0.5 times 1 divided by 3 divided by 18. Actually, I get, what happened? Oh, I forgot to multiply by 5. 2 5s. Yep, no, I just get 231 newtons because it's kilograms meters per second squared is what it should come out to. And then times another meter for length, right? So it should just be newtons, I believe.
And then also, someone's asking,
sorry, I see why they asked that. I didn't. Okay, I didn't square the 1,000. Hang on a second. I see where you're going here. Should that be kilonewtons? Oh shoot, I wrote down newtons on my notes. Yeah, this does get squared. Okay, no, I guess I stand corrected. This probably should be kilonewtons. That doesn't seem right though, just from the perspective of how much a kilonewton is. And we're only going across half a meter. Like that is a lot of force or a lot of torque to have to hold in place. But you have to square this because this is millimeter squared. That's millimeter squared. Get it into meter squared. All right. Well, but this is squared also. That's where I went wrong. I didn't write that in. That this should be squared also. So now, now we're back to newtons because, because they're both squared. So sorry about that. Thanks, Alexi.
And then also someone asked, in this problem, are V theta and U in the same direction since we use the positive R cross V?
Oh, good question. So let's go back. Oops. Okay, so right. We did not put a negative in front of that R multiplied by V. I almost said RV, but so let's go back to this. So V theta and U we use the positive when V theta and U are in the same direction. Otherwise, we use a negative. And in this case, V theta should have actually been going in the opposite direction. In other words, we were spinning away. So I wonder if I left the negative out. Let me take a look at my solution. I did not write one down, but that doesn't mean I did that correctly. So I think you might be right. We're looking at the resistant shaft. Let's say, one other thing real quick. When we go back to this, note that for V theta going out in this direction, the shaft turning is in, that's in the positive direction with respect to the right-hand rule. So that ends up being positive, but U is going that way, V is going the other way. It seems like you should come up with a negative. Just looking at this. Yeah, I think I've confused myself, but it does seem like there should be a negative there. So what that would mean then is that the shaft is going that way. It's got positive. This is the resisting torque. So it's got to go in the opposite direction. It seems like there needs to be a negative out here anyway, only because we are trying to go in the opposite direction. But it sure seems like I was not very consistent about checking on that. So it would have been right in here, right? R times velocity. The velocity ended up getting buried sort of as a Q over A, or 3 times A. But it seems like maybe I'm missing a negative there. I'll check on that and come back to you guys on Tuesday about that. Anything else, Alexi?
Nope, that was all.
Okay, great. Thanks for catching those, guys. You guys are on top of it. Appreciate that. Just the last note here, when this power or W sub shaft or W dot, let me put the dot on that, shaft is positive, power is put into the control volume like in a pump, When it's negative, the power is transferred out of the control volume, i.e. a turbine. So you would use a turbine would create power like you would put into a dam somewhere to allow water to move through it and produce energy, produce electricity. When you are trying to move water, up a system with a pump, you would clearly have to plug that into the wall to get power to make that work. Okay, so last thing here, let's go ahead and get, I've got 3 of these real quick to do these conceptual questions, and then we'll be done for the day. So I think this was one I meant to do last Thursday and we ran out of time. But this is back to linear momentum. A bent pipe is shown in the horizontal XY plane below. A water flow enters at velocity v, goes through the pipe, this 180-degree turn in the horizontal plane, and leaves at the same velocity v. The pipe is supported along its edge as shown. So we've got this support down here. And note that we have an Fy and an Fx, okay? Force is positive in the x and y directions. The correct statement about the magnitude of the force x, F sub x, holding the pipe in place is that F of x or F sub x should be greater than 0, equal to 0, or less than 0. So let's see. Good, we're getting some good response here. I'll let this go for a little bit. I kind of started it early. But based on this layout, which way does that resisting force need to be to support this bend, this 180-degree bend? $77 folks online. Let's see if we get. All right, we might just have 74. Okay, I'll wait till the top of the minute and a half here. 75, that's good. 28, 29, 30. Oh, good. We got 77. Okay, let's go ahead and end there. Let's take a look. Most of you said C, that Fx should be less than 0. 21 of you said it should be equal to 0. And 20 of you said that F of x should be greater than 0, F in the x direction. The correct answer here is C. And the reason for that is that the force, the resulting force that will come from the momentum of conservation of momentum through this bend will push it this direction, which means that Fx in the sort of resultant force that's going to hold it in place needs to go in the opposite direction. So this support force F sub x should be working in the negative direction. It should be negative because the sign convention said that to the right is positive. It needs to be a force that holds in the left direction. Okay, next one. Okay, we'll hide that. Okay, so a fluid leaves the angled arm of a rotating sprinkler as shown. The fluid density is the velocity is blank, and the velocity is v. Let's see, that should have been. Oh well, I don't have a value for that, but we don't really care about the density. Is measured by a stationary observer on the ground. So the absolute tangential velocity of the fluid leaving the pipe is r omega, v cosine theta, v sine theta, v cosine theta minus r omega, v sine theta minus r omega. And I'll just give you a hint. This is the same form what we used in the example just a moment ago. Wait a minute. Which one are we on? This is the absolute tangential velocity. Okay, never mind. That doesn't apply here. It actually is just going to be a really simple version here. Okay, we'll give folks another couple of seconds here.
Is the minus r times the angular velocity, is that like inside the cosine function, or is that like subtracted from the whole thing?
It would be like this.
Okay.
Yeah, both of those. Yeah, thanks. Good question. Okay, we're up to 75, 76, 77. Okay, let's take a look what we've got here. Okay, so I think I misled you with what I was just saying, what I said at the beginning. This actually should turn out to be A. It's just the absolute tangential velocity. That's not the one that we end up using. We ended up using this version of it here because we had an angle, but I think we have some redemption on the next one. So the 6 of you that chose A, good deal. Many of you were probably misled by what I just said with B, and D is another option as well. And this sort of looked like trying to subtract maybe U from V theta. In this case, the absolute tangential velocity is R omega. I thought I had 3 of them. I skipped through them. Sorry about that. So I guess we'll end there for the day. And I hope you guys have a good weekend. Again, we'll have regular office hours on Monday and Wednesday of next week. We'll have rest